Well, hello there everybody. The purpose of this video is that I would like to spend some time reviewing some of the material that we covered in Chapter 7. Upon grading the exams, I found that students fell in generally one or two categories. Either we knew the material really well and were able to score an A or a B on the test, or it seems that we didn't know the material very well at all and we were in the D-F category. There was not a lot of in-between this go around on this test, which is rather odd as we all received the same instruction in class every day. So what I'd like to do is a rarity for me, is I'd like to offer a retake exam for those of you who are interested in taking the retake. In order to participate in this opportunity, you're first going to have to watch this video, take notes on the video. Upon taking notes on the video, present those to me and I will give you a short review assignment to assess how well you were able to take notes and soak up the information in the video. After that, we'll go over the review together, the problems together that you have done for me, and if all looks good, I'll present you with the retake test. And the goal is hopefully we perform much better this go around. And what I'll do is I will just completely replace your old test grade with your new test grade, should you choose to take all the necessary steps to get that far. So with that said, I'm just going to kind of start at the beginning and work my way through the chapter just real quick, of course, because this is an entire chapter condensed into about 20 or 30-minute video. We began the chapter looking at inverses, talking about inverses, inverse relations, leading into inverse functions. And so I'm going to begin right there with this idea of inverses. And to kind of lead us to get into inverses, and I want to see the visual aspect of inverses, what I'm going to do is take this set of points, which is a relation, just a set of points, and I'm going to plot this set of points. So we have a point at 3, 6, 1, 8, -4, 3, 0, 2, and just for visual sake, let's go ahead and just connect the dots just so it kind of pops off the page at us and it makes it a little bit easier to see. Okay, so there's this relation. Now we defined an inverse relation to be one in which all the points, the xy points, are just interchanged, are switched. So the point 3, 6 becomes the point 6, 3. The point 1, 8 becomes 8, 1. The point -4, 3 becomes 3, -4. And the point 0, 2 becomes 2, 0. Now what would that look like, this inverse relation, if I put that on the same graph? So we have this point here at 6, 3, 8, 1, 3, -4, 2, 0. And again, if I just connect the dots so it looks nice and pretty, points look like that. And many of you probably can see it already, and you quite honestly hopefully remember from class that we've talked about this. But if I go ahead and throw in this line here, this diagonal line goes through the origin, has slope of 1, its equation is y equals x. If I throw that line in there, then it should really pop out at you. That in inverse relations, besides the fact that we're just switching the x and y points, we could define two relations as being inverses if they're reflections over this line y equals x, which I think is pretty neat. Now to take that a step further, let's look at inverse functions. Again, the graph is provided because I'd like to give a nice visual of this exercise. So let's go ahead and graph 3x minus 6. It would start at -6 on the y-axis, has a slope of 3 over 1. So we count up 3 and to the right 1. And I get enough points on this that I kind of fill up the graph so that I feel good about it. I'm going to go ahead and connect them with a straight line. Okay, so there is my f of x function. Well, let's find the inverse function to this function. the inverse function, here are the steps. The first step is we rewrite the f of x to say y equals. Okay, so that step's pretty easy. Step 2 is that we're going to take the y and the x, and we're just going to switch them. Oops. So here the x becomes y, and the y becomes x, like that. Okay. Once we've gotten this far, now comes the real math. Now we're going to solve for the y. I'm going to rewrite this to solve for y. So solving this for y, I would add 6 to both sides. That gives me x plus 6 equals 3y. We're going to divide both sides by 3. This is a mistake I saw on the test quite a bit, is that when we were dividing both sides by 3, we were not dividing both terms on this side by 3. We were just getting one term and not the other term. So that was a common error that I was seeing. Divide off the 3's there. So we get 1/3 x, as we've divided that x by 3, plus 2 equals y. The very last step is we're going to write this, this y using function notation. I'll write it as f inverse of x equals 1/3 x plus 2. Now, what should happen when I graph this function is the same thing that happened when we graphed the points in the last section, the last slide, is that they should be reflections about that line y equals x. Start at 2, we go up 1, right 3, up 1, right 3, continue this pattern. Oops, right there, there. And there is our f inverse of x. And hopefully we can see that, but if you can't, you can of course just go ahead and throw that dotted line on there. And it makes it very much more obvious. If I put this line on the graph, this line y equals x, that these two lines are mirror images across this line y equals x. So there's kind of a quick overview of inverse relations and inverse functions. Now we had used this knowledge of inverses to begin talking about logarithms. And I guess I should state for those that are watching this, I know inverses weren't quite the beginning of the chapter. The beginning of the chapter was exponential functions, but I chose to just kind of not include that here, as we kind of, that was background information to get us to logarithms, which is really kind of the heart of this chapter. So we said that logarithms, we define them as inverses of exponential functions. Okay, and really we said that logarithms are just exponents. They're just exponents in a disguised sort of form. Okay, these two expressions right here are saying essentially the exact same thing. 2 to the 5th power equals 16 and log base 2 of 16 equals 5 are synonymous expressions. Okay, to steal an English vocabulary term, they indicate the same idea. All right. Notice that when going from an exponential form to a logarithmic form, there's some commonalities. Okay, the base is the same number in both expressions. Okay, this is a base 2. Okay, the base is the number, the large number beneath the exponent, so this is a base 2. This is a logarithm base 2. Okay, so those are going to match. And then basically you can just see like the 5 and the 16 have switched sides of the equal sign. I guess that's a simple way to look at it. The exponent above the 2 becomes what the logarithm is equal to. Okay, logarithms, when you evaluate them, give you exponent values of the base. Okay, so here's the exponential logarithmic form. Now, because we define logarithms and exponential functions to be inverses, there are some inverse properties of logarithms. These inverse properties of logarithms require, however, that the base, or that the bases match. Okay, the bases have to match. Now if we see these expressions and the bases match, well, because by rule they're inverses, one function will undo the other one, so this log base b cancels this exponential function with base b, leaving just the exponent behind. On the other hand, this exponential function raised to this logarithmic function of the same base, they cancel, leaving behind just the x. Okay, very, very simple idea, very basic idea, but and it's foundational for solving the equations that we're going to get to later in this review video, but the bases have to match. So that is something that we are forgetting when we're getting to the equations. Very easy idea here, and we rarely miss it here, but when we get into the equations, we just kind of forget all about this idea. So they gotta match. Gotta match every time if you're going to apply these properties. And we also talked about some basic properties of logarithms. These logarithms come from their respective exponent properties, but I'm not going to go over those in this video in the interest of time. They were in the original notes, so you can check them out there. I'm just going to give you the log form of these properties, and we'll go over an example of each, and then we'll move on. And we've got a product property of logarithms that says log base b, b can be any number we want, it does not matter, of a product m times n is equivalent to log base b of m plus log base b of n. Okay. Big idea here is that multiplication and addition go together. Okay. When you see multiplication, it expands with addition. Now the exact opposite is true for the quotient property. This says that log base b of m divided by n is equivalent to log base b of m minus log base b of n. Okay, so here we find that division and subtraction go together. Okay, so we got multiplication and addition tie together, division, subtraction tie together. This other property is a power property of logarithms. It says log base b of m to the nth power is equal to n times log base b of m. So the power n is able to move to the front of the logarithm and multiply the logarithm. Alright, let's see these three basic properties and three examples on the next slide. Okay, first example, we see two logarithms of the same base. That's important. These bases are going to have to match. And they're being added. Okay, the addition is important because the addition tells us how we can combine the 12 and the 2.25. Because of the addition, we are going to multiply these two numbers. So that becomes log base 3 of 27. 27 is 12 times 2.25. And now, once we're here, we can evaluate this logarithm by thinking of it as a power, as an exponent. This means 3 raised to what power is equal to 27? The answer is 3. Okay. Next example. We see two logarithms. They are being subtracted. The subtraction tells you what to do with these two numbers. Because we are subtracting, we can divide these two numbers. This becomes log base 4 of 144 divided by 9 is 16. If we think of that as a power, 4 raised to the second power is 16. And this last property is this product property on display here. I don't know what 36 raised to the 13th power is, and certainly you probably do not as well. It's probably much too big to even type into the calculator. But we've got a property that says this is the same as 13 times log base 6 of 36. Now the log base 6 of 36, that's just that's the same evaluation type problem as these here. I'm just thinking of a power. 6 raised to what power is 36? The answer is 2. I can now multiply 13 times 2. The answer is 26. Okay, so there's those three basic properties kind of on display. And we'll see them from time to time when we solve equations that involve logarithms, and that is coming up. All right, next we're going to shift into what I consider kind of the bulk of the material of this particular chapter, and that was on solving equations. The first set of equations I'm going to give you are all exponential equations. Exponential equations have the variable that we're trying to solve for in the exponent of the equation, of the problem, of the expression. So we're trying to solve for that variable. It's located in the exponent. One way to do it is by changing the bases. Okay, we're going to make the bases match. Okay, the bases are 4. Just highlight there, 4 and 64. I'm going to make those bases the same. Okay, and I recognize that, and hopefully you do too. I recognize that 64 is a power of 4. So 64 gets replaced with 4 cubed. Okay, just like that. 64 is 4 cubed. On the other side, I can leave 4 just as it is. 4 raised to the 2x minus 3. I further go one more step here. 4 raised to the 2x minus 3 equals. We've got an exponent property that says if we have a power that is raised to a power, that we can multiply these powers together. So that's going to give us 4 raised to the 3x plus 12. Okay, once the bases are the same, if the bases are the same, then what that implies, what that means, is that the exponents above those bases are also the same. So at this point, I just kind of ignore the bases, and I set the exponent 2x minus 3 equal to the exponent 3x plus 12, and we solve this equation for x. I'm going to take this 3x over here by subtracting 3x, take this minus 3 to this side by adding 3. That gives me negative x equals 15. We'll divide by the negative sign, the negative 1, and we get x equals negative 15. Okay, that is solving an exponential equation without the use of logarithms, and I do that every single time that I notice that the bases can be made to match. Also, now you might be saying, what can I do if the bases can't be made to match? So here we see a base of 5 and a base of 31, and 31 is a prime number. I certainly can't write that as 5 raised to a power. So what we're going to do is rewrite this problem by taking a logarithm of both sides. Okay, so notice that the equation is still there, right? The 5 raised to the 7 minus x and the 31, they're still there. We just put a logarithm in front of each side, and as long as I do the same thing to each side, that's perfectly fine. I can do that. Well, now I've got a 7 minus x, which is in the exponent of a logarithm now, and I can use the logarithm property to pull that exponent to the front. 7 minus x moves to the front of log 5, and that equals log 31. From here, it just becomes an algebra equation to solve. The log 5 is multiplying the 7 minus x, so we can divide by log 5. So we get now 7 minus x equals log 31 divided by log 5. And if you want to go ahead and go to the calculator here and just compute that number, I'm just typing this into the calculator. There's no magic here. I get that fraction is 2.1337. I would say use at least 4 decimal places of accuracy here. Now we're going to continue solving. I subtract the 7 from both sides. So we end up with negative x equals, subtract 7 from that number, and I get negative 4.8663. I'm going to divide by negative 1, and we get x equals positive 4.8663. Okay, so that's the procedure every time we can't make the bases match. We use logarithms to help us solve that problem. Alright, finally I want to show you an example of an exponential equation that involves our natural base e. And again, this is something that we did talk about in class, so I'm not going to reteach what e is, how we develop e. I'm going to assume you have some good working background of what e is based on the lectures in class, so we'll just kind of dive right into this problem. The first thing that we need to do is we need to isolate the e. Okay, so let me take you down a few lines of work here. I need this to say e raised to the 3x equals. Okay, so the extra numbers that are not part of the e need to move to the opposite side of the equal sign. So I'll start by adding 13 to both sides. And that gives me now 4e raised to 3x equals 20. Now we'll divide both sides by that 4. That gives us e raised to 3x equals 5. Okay, at this stage we're going to do what we did in the previous problem. We're going to use a logarithm to solve, but we are specifically going to use the natural log. So I want natural log of e raised to 3x equals natural log of 5. Now, why use natural log? Well, because natural log and e are inverse functions, and so when you place one in front of the other, it cancels it out. So we have now that 3x equals natural log of 5. We can finish this problem by dividing by 3, and we get x equals, or is approximately equal to, I get 0.5365. Again, 4 digits of decimal accuracy is preferred here in all these problems. Okay, next we're going to look at how do we solve equations that have logarithms in them. Our logarithmic equations is what we would call these. Well, the answer is that we're going to use bases. We're going to turn these into like exponential equations. Okay, what I'm going to do is rewrite this problem so that it looks like this. I'm going to rewrite it as 4 raised to the log base 4 2x plus 5 equals 4 raised to the third power. So I went ahead and rewrote the whole thing just so you could see kind of exactly what's happening here so it doesn't get too sloppy. Basically, I left the equation the same. It's here in green. Okay, I didn't change that part of it. All that's still there. But all I did is I put a 4 beneath this side and a 4 beneath this side. Okay, those bases have to, okay, so I'll write here kind of two things here. I must do to both sides. That's something a lot of us were forgetting on the test. Okay, and must match the log's base. Okay, if you do not do those two things, this will not work. It's not correct mathematics if we do not do those two things. Okay, so 4 raised to log base 4, what happens here is that those cancel out. So now we have just 2x plus 5 equals 4 cubed, which can be evaluated to be the number 64. And now we have a very simple algebra equation to solve. We can all do this. Subtract that 5, giving us 2x equals 59. We divide by 2, giving us x equals 59 halves, or if you prefer decimals, 29 and a half. Next, I want to show you a logarithmic equation that will apply one of the properties of logarithms that we previously have discussed. Here you notice we've got two logarithms on this side of the equal sign. We've got to combine these two logarithms. Let's put it out here as a bullet point. We've got to combine the logs into one log. Okay, so that's step one. We're going to put these two logarithms together into one logarithm. And if you recall from a few slides ago, the sign here tells you how to connect these two numbers. When it's addition, we multiply. So this will be log of 8x equals 2. Okay. Now back to the two bullet points to the last slide. We're going to eliminate this logarithm by placing a base underneath it. We're going to do it to both sides, and we're going to match the base of the logarithm. This is a logarithm base 10, so I need to place a 10 beneath both sides. 10 cancels, log base 10, and so now we have 8 times x, or 8x, equals 10 squared, which is 100. We divide by 8, and we get x equals 25 halves. Or again, if you're a decimal fan, 12 and a half. Alright, this last problem I want to do that involves a logarithmic equation is one that involves a natural log, just so we see that. Specifically, this equation has one logarithm, but it's not alone. Okay, so bullet point here. I'm going to say get log by itself first. Okay, so this minus 9 needs to add to the other side of the equal sign. Okay, so this becomes natural log of the quantity 4 plus 3x equals 4. Okay. Now, 2 slides ago, 2 bullet points. Okay. We're going to raise this up above a base to both sides. That's important. Both sides, and we got to match the base of the logarithm to cancel it out. Okay. Natural logs are logs base e, so we're going to use e to both sides. The e cancels the natural log, giving us simply 4 plus 3x equals e to the 4th power. I'm going to solve this by subtracting 4 from both sides. So I've got 3x equals e raised to the 4th power minus 4. Those 4's are different. This one's an exponent, this one's just a 4. And then we're going to divide by 3. We'll get x equals. On the calculator, I'm going to type in e raised to the 4th power. I'm going to take away 4. I'm going to divide that by 3. I'm going to use 4 decimal digits of accuracy. I get 16.8661. The final thing that we talked about in this chapter was the compound interest model, and we went over 2 of them, but one of them we spent much more time on than the other. Both of these models compute the amount of money in an account. If you start with, I'll say that P is the money that you began with. Really stands for principal. Okay, that's why we use letter P. R is the interest rate. T is the time in years. And then you notice they differ from there. Okay, those are the commonalities between the 2 equations. The difference is that this one's got in it. We use this one for in compoundings per year. Okay, this one does not have in. This one we use for continuous compounding of interest. Okay, that's the difference between the two, continuous versus n times per year. Now, for the purposes of this particular chapter, again, we mainly focused on one of these over the other one. We were mainly interested in this one right here. So, in fact, on the first test and on the retake test, the only one that you're going to have to show knowledge of and use is this one that we use for continuous compounding of interest. We're not going to use this one up here. Alright, now a typical compound interest problem might look like this. Find the amount of money in the account, so that's the capital A, when $15,000 is invested at 4.35% interest when interest is compounded continuously. That's important. Again, that's the wording that leads us to the right model. The right model here is A equals PE raised to the RT power for 30 years. So we're looking for amount of money. We began with $15,000. E raised to the R. Now the R has to be put in as a decimal. 0.0435 times 30 for 30 years. Okay, once we're typed in here, there's nothing more to do except use the calculator. Use the calculator to evaluate this. And you know, if you're watching these notes at home, don't just type down my answer, write down my answer. You need to get a calculator out and type this in and see if you can actually type in the expression correctly, because there's one thing to be able to write it down here correctly, but if we can't actually compute the right answer, then what is this even giving us? What is this even doing for us? So practice this. I get $55,315.34. That's the amount of money in the account after the starting information is applied. Okay, one final problem that I'd like to go over. It's another application of the compound interest formula, the continuous compounding of interest formula, but we're not actually solving for the amount of money in this case. This is asking the question, how long would it take? How long would it take is asking us about the value of time. How many years would it take? We're going to be solving for t in this case. And so what do we know? We know that our money is going to triple at this interest rate, compounded continuously. Again, it's the continuous wording that leads us to the correct model. A equals P E raised to the RT. Okay, so we plug in the numbers that we have. The trickiest part of this, I suppose, that most people find the trickiest is this, tripling. Okay, so the question is, what's P when that's all it tells us, that our money is going to triple? Well, it actually doesn't matter. Okay, it doesn't matter at all. You pick a value for P. Anything you want. Okay, so whatever makes you happy, that's what you pick. Okay, we'll just go with that. So let's say that you pick $100. You're going to invest 100. E raised to the 0.0575 t. Now your money's tripling. So I chose 100. It triples to 300. Okay, it's that easy. Now we solve this. I'm going to divide by 100 first. 300 divided by 100 is 3. E to the 0.0575 t. This is why it didn't matter. Why you can pick whatever p you want. Because since we're tripling, whatever number we put here, if we triple it correctly, when we divide by that number, it's always going to reduce to 3. Every time. So it doesn't matter what you pick. Pick what you want. A lot of people, once they've done this enough times and they know what's always going to happen, they simply just pick 1 and 3, and $1 triples to $3. And you don't even have to write anything here, therefore you won't even have to do the division. But whatever you want to do. Well, now we've got an equation that has e in it. And we know that when we have e in the equation, we use a natural log in front of the equation will cancel the e. Natural log cancels e, so we end up now with natural log 3 equals 0.0575t. We can divide by that decimal, 0.0575. And that's going to solve our problem. We're good. I'll do it over here. T equals, this is again calculator work. I'm typing in natural log of 3 divided by 0.0575. Do that on your own as well. Make sure you can get this right. I get 19.11 years. All right, well there it is. Your quick review on Chapter 7. Again, just to reiterate, if you want to take the test, retake the test, you have to have 1, taken notes over this video. 2, you're going to bring those notes to me and let me see them. Okay, I want to see evidence that you did take notes, that you put in the time outside of class to review the chapter. After that, and I see your notes, and I will give you a short review assignment. It's not going to be very big, short, you know. Maybe give you an example or 2 of everything you saw in the video, just to practice on your own, see how well you're doing. After that, you finish that review assignment, you bring it to me, we'll look at it together, we'll check the answers, we'll diagnose if there's any mistakes or anything else we still need to polish up. And after that, once I feel like I know without a doubt that you're going to improve on your test, and you know that you're going to improve on your test, then we'll let you retake the test. Simple as that. If you do better, which you will if you follow these steps, if you do better, we'll just replace the old score with the new, better score. So that's it. Good luck. I hope you take advantage of this, and let me know how it goes.